So you recall from our previous video that in Chapter 2 we're going to have a bunch of topics, one of which is going to be the characteristics of single individuals drawn from a normal population with a known mu, known value of mu sigma. And then we're going to move on to trying to draw inferences about population means, in which quite obviously mu is going to be unknown because that's what we're trying to draw inferences about. But in the initial case, we're going to think of a situation where the population standard deviation is known. And then we're going to move on to drawing inferences about the population mean. In a more realistic case, whereas before, mu is going to be unknown, because we're attempting to draw inferences about mu, but now sigma as well is going to be affirmed to be unknown, and we're going to estimate sigma with the sample standard deviation, or S. And this is what we went over in the last video. And it's really a bit unrealistic. I cannot believe that any time in your own research you will ever have to do anything like this. Why did we go over it? The reason for going over it was to get you familiar with the Z-test and the Z-table, because we're going to be using that as we go over these topics. So we're going to begin in this video with this topic. We're not going to cover the entire topic. We're going to only cover the first two subsections. So we're going to be talking about 4.1, which is an overview of this chapter, and section 4.2 or subsection 4.2, which is rules of variance. So I just want to give an overview of this topic, estimating population means when you've got a known population variance. So let's go and think about kind of an example that we alluded to earlier. Let's say we're interested in female heights of those that are registered at the University of Alberta in the fall of 2020. And you can imagine we could have a list of all those students and all those student heights. And we could take a sample. We could take a sample of 10 individuals. So maybe this one, this one, this one, this one, this one, and maybe you get, in terms of centimeters, 123, 138, 125. Maybe we sample a whole bunch more, so we get 10, and we calculate y bar, the average of the 10 different heights of the individuals that we sampled. Well, we could do that again on another day, or a different person could do that on the same day, and they would sample 10 other people and get 116, 132, 121. They would get maybe a y, whereas these would get a y bar of 124. Maybe here we get a y bar of 127, and we could index this as with a 1, and this is a 2, because this is the first value that we got of y bar, and then here's a second possible value of y bar. Now let's go back and think about this concept of an experiment and a sample space. And we can consider our sample space as being all possible samples of size 10. And then we're going to come on to this really important concept of a random variable. What's a random variable? Well, a random variable is a function that maps or translates the outcome of an experiment into a number. So here the random variable is the average height. And remember, we made a big deal, or I made a big deal, about the distinction between y, the outcome you get in any one experiment, and capital Y, the set of all possible outcomes that might have been obtained. and we said, okay, there's an alternative way to think about this concept of random variables. We can, on the one hand, think of it as the mapping or the translation it goes from an outcome to a number. But we can also think of the random variable as being the set of all possible outcomes that might have been obtained. So with that in mind, it's helpful to think about the distinction between y bar, when we actually do the experiment, select our 10 individuals, and calculate their heights. So the actual value when the experiment is done and contrast that to capital Y bar, which is a set of all possible outcomes. And by now you should realize what is Y bar. Y bar is a random variable. And more than that, obviously it is a continuous random variable. And so what do we know about continuous random variables? Continuous random variables have what? They have probability, density functions. So, first point I want to make is that the set of all possible y bar, i.e. y bar, is a random variable. And as such, it's going to have a probability density function. But we're going to give a special name to it. We're going to give it a special name, and that special name is sampling distribution. Why does it get this special name? Because it's the PDF of a sample statistic. Because you remember that any individual lowercase y bar that we calculate is just a sample statistic that we get when we take the sum of all the yi and divide by n. And the third point is what we're eventually going to see is that the sampling distribution, when samples are taken from a normal population, is itself going to have a normal distribution. And it's going to have a normal distribution, and as such, it's going to have a standard deviation. And we've got a special term that applies to the standard deviation of a sampling distribution. And that special term is, in the case where we're trying to draw inferences about the mean, the standard error of the mean, or just the standard error. So that's just a few introductory comments made as an overview. Now I want to go over section 4.2, which are some rules of variance. And up until now, I've been using that as a single symbol for standard deviation and that as a symbol for variance. Now I'm going to use STDV as the symbol for standard deviation and variance as a symbol for variance. Why am I doing this instead of that? These symbols are typically associated with a normal distribution, whereas these symbols, they're associated with any distribution. And although the focus of this course is going to be on the normal distribution, the rules that I'm going to go over are going to be applicable to any distribution, and that's why I wanted to use these more general symbols. So, what are some of these rules of variance? Well, the first rule is if you've got a constant A, that the variance of A is equal to 0. And that sort of makes sense. If I gave you the number 115, what's its variance? Its variance is 0. Not surprisingly, as a corollary, what's the standard deviation of a constant A? That also is going to be equal to 0. That's the first rule. The second rule is that the variance of some random variable y plus a constant A is going to be equal to the variance of y. So what this means in a practical sense is if we've got a bunch of numbers and we add a constant, let's say 17, to all those numbers, the new number that's created is going to have the same variance as the old number. And let's just think of a very simple example that shows this. Let's say our original numbers were the values 2, 4, and 6. So that's a population. What's the variance of those three numbers? Well, the mu is going to be equal to 4. So if we think of what variance is, it's the mean of the squared deviations. So what's the mean of the squared deviations going to be? It's going to be 2 squared plus 0 squared plus 2 squared over 3 is equal to 8 over 3. And now what I'm going to do is I'm going to add a constant to each one of those. So let's say I add a constant of 20 to each one of those, and I get 22, 24, and 26. Now what's my mean? Now my mean is 24. So let's calculate the variance once again. What's the variance? It's the mean of the squared deviations. So it's going to be 2 squared plus 0 squared plus 2 squared over 3, which is equal to 8 over 3. So I've shown the point is if you've got a random variable y and you add some constant to each individual in that series of random variable, that the variance of the new variable that's created is going to remain unchanged. Okay, the next rule. The next rule is variance of some constant A multiplied by y is going to be equal to that constant squared times the variance of y. So if we've got some random variable represented by capital Y, and for each one of those values, we multiply it by a value, let's say, of 3. So we now look at this new variable that's been created by the multiplication of 3. Its variance is going to be 9 times the variance of the original variable. So let's just work through that with a very tiny, simple example. So let's go back to 2, 4, 6, and we saw its variance. The mean is equal to 4 was 2 squared plus 0 squared plus 2 squared over 3, and that was equal to 8 over 3. Now we're going to multiply each one of these by 3, so we're going to get 6, 12, and 18, and now the mu is equal to 12, and we think of the mean squared deviations. Well, the difference between 12 and 6 is 6, so you're going to get 6 squared plus 0 squared plus 6 squared over 3, and that's going to be equal to 72 over 3. So what's the ratio of these two numbers? Well, this variance is 9 times larger. So what we saw was we multiplied y by 3, the variance of 3y was increased by a factor of 9. Factor of 9, or 3 squared. And that's the point that we wanted to make. So that when you have a random variable, you multiply it by a constant, the way you calculate the new variance is to take that constant, square it, and multiply it by the variance of the older constant. So now we can think about the concept of standard deviations. And when it comes to standard deviations, the standard deviation of A times Y is going to be equal to A times the standard deviation of Y. So again, we go back to our simple example. If we think the standard deviation of 2, 4, and 6, that's going to be equal to the square root of the variance of 2, 4, 6, which is going to be the square root of 8 over 3, and the standard deviation of multiplied by 6, 6, 12, and 18 is going to be equal to the square root of 72 over 3. So if we think about the ratio of these two numbers, the ratio of these two numbers is going to be square root of 72 divided by square root of 8, which is square root of 72 over 8, square root of 9 is equal to 3. So what we've shown is, with this little example, is if you've got a random variable y and you multiply every occurrence of that by a, you get a new bunch of numbers. That new bunch of numbers is going to have a standard deviation equal to that constant a multiplied by the standard deviation of the original variable. So those are just some rules of variance. The next topic we're going to talk about is the sampling distribution of means drawn from a normal population.